Imagine holding the power of a star inside a machine here on Earth. That is the basic dream behind fusion energy. In the sun, gravity squeezes hydrogen until atomic nuclei combine and release enormous energy. A fusion power plant tries to recreate that process in a controlled reactor, not with gravity, but with heat, plasma physics, and magnetic fields. The fuel becomes an ultra hot plasma where electrons are stripped away from nuclei and the gas behaves like a glowing electrically charged fluid. The real challenge is not just making fusion happen for an instant. The challenge is guiding that plasma, capturing the energy it releases, and turning that energy into useful electricity for homes, cities, factories, and the grid. In this video, we will follow the full path from star-like plasma to fusion reactions to heat, steam, turbines, generators, and finally clean electric power. At the heart of many fusion reactor designs is a device called a tokamak. It looks like a giant donut-shaped chamber built to hold plasma without letting it touch the walls. The common fuel mixture is deuterium and tritium, two heavy forms of hydrogen. To make them fuse, the fuel must be heated to temperatures far beyond the center of the sun, often above 150 million degrees Celsius. At that temperature, matter becomes plasma. The nuclei are positively charged, and because charged particles respond to magnetic fields, powerful superconducting magnets can shape and confine the plasma. These magnets create invisible highways that guide the particles around the chamber. That magnetic cage is essential because no solid material could survive direct contact with plasma that hot. Instead of holding the plasma with a physical container, the reactor holds it with carefully controlled fields. Now let's zoom down to the atomic scale. In a deuterium-tritium fusion reaction, two hydrogen isotopes collide with enough energy to overcome their natural electric repulsion. When they fuse, they form a helium nucleus and release a high-energy neutron. This is the key energy carrier in many fusion power plant concepts. The helium nucleus is charged, so magnetic fields can keep it inside the plasma, where it helps maintain heat. But the neutron has no electric charge. That means the magnetic field cannot hold it. It flies straight out of the plasma and passes through the magnetic cage. This may sound like a problem, but it is actually part of the design. The escaping neutron carries most of the reaction energy away from the core, and the reactor is built to capture that energy in the surrounding structure. Surrounding the plasma chamber is a special layer often called the blanket. In many designs, this blanket contains lithium. When fast neutrons from the fusion reaction slam into the blanket, their kinetic energy is absorbed and converted into heat. The lithium also plays another important role. It can help produce more tritium fuel, which is needed to keep the reaction cycle going. But from the point of view of electricity generation, the main point is heat. Fusion does not usually send electricity directly into wires. Instead, the reactor first turns nuclear energy into thermal energy. Coolant channels carry that heat away from the blanket, protecting the machine and moving useful energy to the next stage. In other words, the plasma creates energetic particles, the neutrons escape, the blanket absorbs them, and the coolant becomes the bridge between the fusion core and the power plant. Once the coolant carries heat away from the reactor blanket, the system begins to look more familiar. The hot coolant transfers energy into a heat exchanger where water is turned into high-pressure steam. That steam rushes through turbine blades, forcing them to spin at high speed. The spinning turbine drives a generator, and inside that generator, motion becomes electricity through electromagnetic induction. Magnets and coils interact, producing an electric current that can be conditioned and delivered to the grid. So even though the fusion reaction itself is incredibly advanced, the final electricity step is based on a proven principle used across many power plants today. The difference is the heat source. Instead of burning coal, oil, or gas, a fusion plant aims to use star-like reactions with very low carbon emissions, abundant fuel sources, and no long-lived chain reaction that can run away, like in conventional fission reactors. So here is the full journey. Fusion begins by heating deuterium and tritium until they become plasma. Magnetic fields hold that plasma away from the reactor walls, giving the nuclei a chance to collide and fuse. Each successful reaction creates helium and releases an energetic neutron. Because that neutron is uncharged, it escapes the magnetic field and enters the surrounding blanket. There, its energy becomes heat. Coolant collects that heat. A heat exchanger makes steam. The steam spins a turbine, and the turbine drives a generator that produces electricity. That is how a plasma reactor can turn the physics of stars into power for the grid. If you enjoy clear explanations of advanced energy technology, make sure to subscribe, like, and share this video. The future of power is being built step by step, and you will want to keep watching. For more information, visit www.globalpowernews.com. My YouTube channel is Nawaz Lakho Power Pro. Do not forget to subscribe, like, and share.